All right, let's get into chapter 19 now. This is the first of two chapters where we're going to be investigating and learning about the applications of differential calculus. So the good news, I guess, is that most of the problems we see in chapter 19 and 20 are going to involve much simpler derivatives than a lot of the super crazy algebra ones that we saw in chapter 18. But the bad news is that now we have added context. So we need to really start thinking about what things mean in the context of the question. And spoiler alert, it mostly has to do with slopes of tangent lines. And that's certainly what we'll be looking at, especially in chapter 19, because 19 is all about properties of curves, as you can see. And the idea here is that we're going to be able to, by the end of this chapter, graph a whole lot of crazy functions that up until this point in our lives, we've only been able to do with the help of technology. But through the wonders of calculus, we'll be able to get very nice sketches. Anyway, this video is going to be pretty straightforward and easy. We're only going to look at section A, tangents and normals. We've been talking about tangent lines for a while. Normal is the only word here that might be new to you, but let's see what this is all about. Okay, I mentioned this in a previous video, that if we want to write out the equation of the tangent line, my preferred method is this right here. We're going to use point-slope form. We don't want to waste time trying to write something in slope-intercept form. If you're really comfortable with a standard form of a line, you can quickly jot that down once you know what the slope of it is. But if you're unfamiliar with those shortcuts, I don't think it's worth it. We can have an interesting conversation about that once we get up to chapter 15, but that's not going to come for a while if we're progressing in the course in the order that these videos are in. That's in year 2. So for us, I think we're going to focus on point slope. And the idea with that, again, is we're going to be told we want to find the equation of the tangent line at a particular point, which in this image is this one right here, point A. So it has coordinates A, f of A. So we're just going to put those in here into point slope, and then we're going to be calculating the derivative of the curve f of x, whatever it is, evaluating that derivative at A, and that's going to give us our slope. All right, that's easy enough to do, I think. And the normal is just as easy. The normal is just perpendicular to the tangent at the point of tangency, which means that if I wanted to write the equation of that line, then its slope is going to be the negative reciprocal of the tangent line. All right, that's really all that there is in section A. So we'll just spend a few minutes now going through a whole bunch of examples. They're just, some of them will just be worded different ways, just so we can get used to how questions might be phrased. This first one, very straightforward. Find the equation of the tangent line at the point x equals 1. I think it's a good first step to just ask, if x equals 1, what does y equal to? Pretty obviously from this equation, y is going to be equal to 2. Let's use that. We're going to then also, yes, so we got the point 1, 2. We then take the derivative. The derivative of x squared plus 1, super easy, that's 2x. We substitute 1 into that because we know that x is equal to 1. 2 times 1 is 2. So now we know that the slope is 2. We're ready to go. We've got the slope, we've got the point. That means we can write point slope. Textbook, a little lame. It's not writing it out in the format that I wanted, so here it is. I would just leave my answer exactly like this. If you want to distribute that 2, you'll get this line. If you want to move everything over, you'll get that line. They're all the exact same equation. I like the circled answer. Easy. Let's keep going. Here we go. Second one, I think an easy mistake to make is just to not read the question carefully enough. You might see, oh, I've got a function, I've got a point, let's go, same as the last one, but just be careful. It says the normal, not the tangent. But other than that, this is very straightforward. Again, we want to figure out what the y value is at the point that we're interested in. So it ends up that it's also 4. So we've got our point. Now we're going to find the slope of the tangent, and then just take the negative reciprocal of that. So we rewrite our function in exponent form, so we got 8 times x to the negative 1/2. We use power rule. That gets us here. We substitute in the value for 4 into that. Square root of 4 is going to be 2. 2 cubed is going to be 8. But it's really to the negative cube, so we have 4 divided by 8. It's going to be 1/2. Yeah, or negative 1/2, excuse me. So that's the slope of our tangent, which makes the slope of our normal equal to positive 2/1. So then our equation just becomes either of these two. Here they're using the standard form trick that I kind of referenced earlier. I'm not going to talk about that. But for me, I think the answer down there, y minus 4 equals 2 times x minus 4, is the appropriate one to use. Find the equations of any horizontal tangents to this function. Okay, if it's a horizontal tangent, that means that the slope of the tangent is going to be equal to 0. Let's keep that in mind as we go through here. So now we don't have a point. We're going to have to figure out where that point might be. So, and by the way, we're going to see a picture of it over here. We're pretending that we're doing this without a calculator. If we have a calculator, then it's a little bit easier. I'll reference that at the end. So step 1, we've got the function, and we're finding out its derivative. Since we want the horizontal tangent, we're going to set that equal to 0. That's a very easy quadratic. No problem. We're going to factor it out. From there, we can see we're going to have x is either plus 2 or minus 2. For each of those, we're just going to substitute those in to here to figure out the y value that gets matched up with them. When x is 2, we've got negative 14. At negative 2, we've got 18. And that, by the way, is all that we need to know. Since it's a horizontal tangent line going through those points, those y values are exactly the equations that we're interested in. There we go. Now, if I had access to a calculator the whole time, then, I don't know, maybe it's faster, instead of taking the derivative and setting the derivative equal to 0, perhaps it's faster just to calculate the maximum and the minimum point on the graph if I can see them. It's up to you. But this idea of setting that tangent equal to 0, setting the derivative equal to 0, that's going to be a big concept coming up in the next video. But let's not get ahead of ourselves. Here's one more. Show that the equation of the tangent is equal to y equals e times x minus 2. All right, whatever. We've got the answer in advance. No problem. We can just progress as though we had no idea. This one's a little bit different because they give us a y value. But we can still work that backwards to figure out the x value. If we've got negative 1 is equal to ln of x, that means that e to the negative 1 is equal to x. In other words, x has to be 1 over e. So now we have our coordinates, 1 over e, negative 1. And then let's just show this. Here we go. We've got 1 over e. And then we're going to take the derivative. We know the derivative of ln of x is just 1 over x. So we substitute in our x value. 1 divided by 1 over e is just e. So that gives us the slope of the tangent line, which, whatever, it can be. And that's it, right? So we got point slope form. Here we go. That's what I wanted to see. Yeah, y plus 1 is equal to e times x minus 1 over e. And when you distribute and move things over, we get the equation that we were told to find. We need to know our trig. So just throwing this in here just to make you think about that a little bit. Again, we're given the x value here. So if we put pi over 4 into tangent, what is the tangent of pi over 4? That's going to be equal to 1, right? So that gives us our point. Now we take the derivative to find the slope. So the derivative of tangent is secant squared. I'll forgive you if you don't know what the secant of pi over 4 is, but you know, instead of writing secant, we can just write it as 1 over cosine. And now you should know what the cosine of pi over 4 is. So you might know it as 1 over the square root of 2. I know it as the square root of 2 over 2. It doesn't make a difference. Of course, when we simplify this, we're going to get 2 either way. So we've got our point, we've got our slope, and So we go through it and get our final answer. Again, none of these answers are what I would write. I'd be writing what y minus 1 is equal to 2 times x minus power 4. That would be my perfect answer. All right, so this is different. Find the coordinates where the tangent meets the curve again. Remember that a tangent line, it doesn't need to touch the graph only once. It means that it touches the graph perfectly at that one particular point, but it might intersect it elsewhere. So I still have a tangent line at that point, even though it has a second intersection later on. Otherwise, I mean, if that wasn't the case, then many curves we couldn't possibly be talking about tangent lines. But often we forget about the fact that tangent lines might intersect a curve later on because we're always just so focused on that one point that we don't stop to like zoom out and really take it all in. So here we're going to have a tangent line that touches the curve elsewhere. Oh, same idea with asymptotes, right? We talked about asymptotes earlier in this course. An asymptote just means that when x gets really, really big or really, really big in the negative direction, that the y value gets closer and closer to that asymptote. But of course, we could have a graph that, you know, crosses over an asymptote and then eventually gets closer and closer to it later on. We don't care that it crosses the asymptote earlier. What all that matters is what happens in the end. Anyway, let's do this problem. So we've got the curve. We even got the point. We're interested in 1, 4. So I guess we should figure out what the slope's going to be there. So we're going to take our derivative, easy to calculate. Substitute in 1 as the x value, very easy to do. Our line is going to have a slope of 4. So now we've got, hang on, we've got this curve here. We're now about to have a second curve, which has a slope and a point. Oh, and we want to know where they meet again. Oh, this is just like a system of equations. We're going to figure out where they meet. As before, I would have had this as y minus 4 is equal to 4 times x minus 1, but you can see that's going to be the same thing. Simplifies very nicely to y equals 4x. So now we're solving x cubed plus x plus 2 equals 4x. So this might be a paper 2 question because for the most part we don't know how to solve cubics. But whatever, we could just grab a calculator and we could easily figure out where they intersect again. I don't know, the book shows us 3 different images here from different calculators. You can see the intersection point is -2, -8. So that's the answer here. But if you're a little suspicious about that integer answer, yeah, you know, we could have actually solved this by hand. We're solving the top equation. We can bring everything over to the left-hand side. Now we're solving a cubic. It's not something that we necessarily have a procedure for, but we already know one of the answers, right? We already know that these intersect when x is equal to 1, which means that I know that one factor of this cubic is x minus 1, going back to chapter 6. Yes, which means we can use long division here to figure out what we get left over when we divide by x minus 1. There's no remainder. This is great. We get this quadratic. So these two multiplied together give us the cubic. And turns out that this quadratic, that actually factors really nicely. That factors out into x minus 1 again and x plus 2. So it turns out that our original cubic, this is just equal to x minus 1 squared times x plus 2. And right there we've got our answers where they intersect. It's 1 or -2, and -2 is the answer that we're looking for in this problem. So that was pretty cool, right? Maybe. Next, this one's definitely very different, right? So we're going to try to find the equations, oh my gosh, of the tangents. There's more than one to this curve, which is, gosh, like the simplest curve we could look at, so that's good, from this outside point. So if you're uncertain how there could be 2 tangents, just try to draw pictures. Imagine perhaps a parabola in your head and a point outside of it. You're going to have one tangent kind of like above the point and one kind of below it. We'll see a picture show up in a second, but they only actually draw in one. I'll fill in the other so we can see it. So, okay, here's a whole lot of stuff. Here's our point, right? And we're just, in our work right now is kind of solving for the first tangent line. So we're going to say that the tangent goes through some generic point on the curve. So we can imagine that it's this one down here. If it's on the curve, y equals x squared, then we can say it has coordinates a squared. Okay, that means that the slope at that point is going to be 2 times a. So we've got our slope. And we've got a point. So we could say that the slope of the tangent line is down here. Or sorry, the equation of the tangent line, I should say. It's down there. But we got to figure out what a is. So we know that it goes through 2, 3 also. So that means that we can substitute in 2 and 3 for x and y, and then we're just going to solve this equation for a. It's a quadratic in a, so we're getting 2 answers, which makes sense since we kind of assumed from the beginning that there's going to be actually 2 tangent lines, and I forgot. I promised you there'd be another one, so you can probably see it. It should be someplace up here. I don't know. Picture is not drawn to scale, right? We could have a second line, maybe that's tangent like that. Anyway, solving that quadratic, we've got our 2 values for a, and then we can just dump those back into the equation that we have right here, giving us the 2 answers that we have down there. Woo! Anyway, that's hey, that's 19a. So just a whole lot of stuff with tangents and occasionally normals. I mean, most of the problems we see will be about tangents, but normals will pop up from time to time. I feel like they're always just like a gotcha question, like, oh, you didn't read all the words. You did all this wonderful math for the wrong line. There's not, I don't know. In my experience, there's not too much of interest at this level of calculus with normals. They're just a thing to study just because. But we'll see when we get up to, we'll talk about it a little bit in chapter 14 and 15. Here we're discussing normals to a curve, but later on when we start thinking in 3D, we'll also have normals to planes. So like this idea of a normal being perpendicular to stuff is actually a big idea, so that we're just talking about one little tiny facet of it in this chapter, which is why it seems kind of boring and like what's the purpose of it. But it ends up being a bigger thing. So there's normals to planes, there's normals to any other 3-dimensional curvy surface, but that's not even something that we'll discuss in this course. That's for later on in your mathematical career, perhaps. Anyway, I'm babbling on, so I'm going to stop. I hope you enjoyed. If you didn't, I don't care, because I did.